In the last video, we introduced the concept of filter and studied some basic digital FIR filters. Here in this video, we will study some simple digital IIR filters. Now to start with, here we can take HZ as 1 plus Z inverse, which would be an FIR filter. In order to make it an IIR filter, we need to introduce a pole into the system. As from the definition of pole, we know is the point where the system diverges. So we need, for the system to make it an infinite impulse response, we need to introduce a pole to the system. So what we have done is introduced a pole at point alpha, Z is equal to alpha. So what we have done is divided the numerator with 1 minus alpha Z inverse. Now we know in a Z plane, for a system to be stable, we need to have all the poles inside the unit circle. So the value of alpha, the magnitude of alpha, should always be less than 1. Now we need to normalize the DC component, or we can understand this in order to make it into a low pass filter. What we need to do is make the value or magnitude of Hz is equal to 1 when Z is equal to 1. In order to ensure that, we need to introduce a scalar component, that is multiply 1 plus Z inverse by 1 minus alpha Z inverse with 1 minus alpha by 2. That is normalizing the DC component, or to ensure that the value or magnitude of Hz is 1 at Z is equal to 1. So here we can now say that Hz is a simple IIR low pass filter. Now we can replace Z by e to the power j omega, and if we square it, the value that comes up after algebraic calculation would be 1 minus alpha whole square by 2 into 1 plus cos omega by 1 minus 2 alpha cos omega, it would be plus alpha square. Now if we differentiate this with respect to omega, we see that it comes up to be less than 0 in the range 0 to pi for omega. That means in this range from 0 to pi of omega, our magnitude h ej omega decreases or falls monotonically, has a monotonic response. So here we can show that between 0 to pi, magnitude of Hz falls from 1 to 0, and if we increase alpha in the direction mentioned, our curve becomes more towards ideal. We get a better filtering if we go on increasing alpha. Now in order to find the cutoff frequency, we can put the magnitude as 1 by root 2 into the previous equation. So we have 1 by root 2 whole square, 1 minus alpha square by 2 into 1 plus cos omega c by 1 minus 2 alpha cos omega c, plus here it has been changed, that is alpha square. In case of omega, we have replaced it by omega c by the definition of cutoff frequency, where the magnitude falls to 1 by root 2. So from here, after calculation, what we get is cos omega c is equal to 2 pi by 1 plus alpha square. So from here, alpha can be either 1 plus sine omega c by cos omega c or 1 minus sine omega c by cos omega c. But if we take 1 plus sine omega c by cos omega c, then the value of alpha would surpass 1, will be more than 1, which is not allowed for the system to be stable. So the accepted alpha would be 1 minus sine omega c by cos omega c. Similarly, if we want to take a high pass filter, we can replace z by minus z, and what we get is 1 minus alpha by 2, 1 minus z to the power minus 1 by 1 plus alpha z to the power minus 1. or 1 plus alpha by 2, 1 minus z to the power minus 1 divided by 1 minus alpha z to the power minus 1. Both would yield or would guarantee a high pass filter, that is at z is equal to 1 or omega is equal to 0, we will have 0, and at z is equal to minus 1 or omega is equal to pi, we will have plus 1. And the characteristics would be more towards ideal if we go on increasing alpha in the direction shown. Here also omega c would be cos inverse twice alpha by 1 plus alpha square, from where alpha would be same as before, 1 minus sine omega c by cos omega c. Similarly, for band pass filter, the simplest band pass filter that could be designed is the mentioned equation, where now as it is a band pass filter, we will have two cutoff frequencies as shown in the diagram, omega 1 and omega 2, and omega naught is the point or the frequency for which the magnitude is highest as 1. By calculation, we can show that cos omega naught is equal to beta, and omega 2 minus omega 1, which is the bandwidth, is equal to cos inverse twice alpha by 1 plus alpha square. Similarly, for a band stop filter, Hz is equal to 1 minus 2 beta z inverse plus z to the power minus 2 by 1 minus beta 1 plus alpha z to the power minus 1 plus alpha z to the power minus 2 into 1 plus alpha by 2, which is the scaling factor which has been introduced in order to maintain the required values at the required frequencies. Similarly, here after calculation or replacing z by e to the power j omega and manipulation, we can show that the minimum point or omega naught where the magnitude falls to 0 would be cos omega naught is equal to beta, or omega naught would be cos inverse of beta, and the bandwidth, that is the difference between the two cutoff frequencies as we have shown in the diagram, would be the same as before, which is cos inverse twice alpha by 1 plus alpha square. And in all the cases, in order to maintain the stability, alpha should be less than 1. So here we can end the video for today, and in the subsequent videos we will proceed with more concept of filtering.